Introduction to Module 2. Welcome to Module 2 of Database Management Systems. In the first module, we focused on concepts, how databases are modeled, designed, and managed in theory. Now we're going to get hands-on, moving from concept to implementation. In this module, we'll look at how to translate our designs into working databases. Dive deeper into SQL, the standard language for relational databases. Explore forms, reports, and database-driven applications. Discuss database administration, the behind-the-scenes work that keeps systems running reliably. Wrap up with real-world considerations, from scaling to security, and from performance tuning to troubleshooting. By the end of this module, you should be able to design, build, query, secure, and manage a database, whether it's a small personal project or part of a large enterprise system. 2.1 Database Design in Practice. In Module 1, we discuss conceptual, logical, and physical design in theory. Let's now walk through how this happens in real-life database projects. Imagine we're designing a library management system. Step 1, Requirements Gathering. Who are the users? Librarians, borrowers, administrators. What do they need? Borrow books, return books, track overdue items, manage inventory, run reports. What's the scope? Are we only tracking books, or also digital resources, magazines, and event registrations? Step 2, Conceptual Design. We identify entities, books, members, loans, staff. We identify attributes. Books, ISBN, title, author, category, status. Members, member ID, name, email, phone. Loans, loan ID, date borrowed, date due, date returned. We define relationships. A member can borrow many books. A book can be borrowed many times but only by one member at a time. Step 3, Logical Design. We translate this into tables, primary keys, and foreign keys. Table books with primary key book ID. Table members with primary key member ID. Table loans linking both with foreign keys. We decide on data types for each attribute, strings, integers, dates. Step 4, Physical Design. We choose indexing for fast lookups, perhaps index title in books for quick searches, and index member ID in loans for fast retrieval of borrowing history. 2.2 Model Building. In databases, a model is a structured representation of how data will be stored and related. In our library system, we might have an entity relationship, model as a diagram. A relational schema listing all tables and their fields. A data dictionary explaining each field, its type, and constraints. These models are not just for documentation, they are blueprints for implementation. Without them, a database grows haphazardly, leading to duplicated data, inconsistency, and poor performance. 2.3 Data Tables, the core of relational databases. A table is the most basic storage structure in a relational database. In our library system, Books table stores all book records. Members table stores member information. Loans table records each borrowing transaction. When designing tables, we must assign meaningful names, avoid vague names like data1. Define primary keys, unique identifiers for each row. Avoid storing derived or calculated data unless necessary for performance. Use constraints to enforce rules, such as not null, unique, or check. 2.4 Forms and Reports. A database alone is not user-friendly. Most users don't want to type SQL commands, they want forms and reports. Forms provide an easy interface for entering and editing data. Example, a borrow book form where the librarian enters the member ID, scans the book barcode, and clicks Submit. Reports summarize and present data in a readable format. Example, a monthly overdue books report listing all books overdue by more than a week, with member contact details. Forms and reports bridge the gap between the raw database and the people who need its information. 2.5 Introduction to SQL. SQL, or Structured Query Language, is the universal language for interacting with relational databases. It has two main categories. Data Definition Language, DDL, commands for defining structure. Create table, alter table, drop table. Data manipulation language, DML, commands for handling data. Insert, update, delete, select. Example, creating a table. Imagine creating the books table. SQL. Copy. Edit. Create table books. Book ID int primary key. Title var char, 255. Author var char, 255. Category var char, 100. Status var char, 20. Example, inserting data. SQL. Copy. Edit. Insert into books, book ID, title, author, category, status. Values 1, 1984, George Orwell, fiction, available. 2.6 SQL queries in practice. SQL queries allow you to retrieve exactly what you need. Basic retrieval. SQL. Copy. Edit. Select title, author from books. Filtering results. SQL. Copy. Edit. Select title from books where category equals fiction. Sorting results. PGSQL. Copy. Edit. Select title, author from books ordered by author ASC. Joining tables. PGSQL. Copy. Edit. Select members.name, books, title. From loans. Join members on loans.memberid equals members.memberid. Join books on loans.bookid equals books.bookid. This join pulls together member names and book titles for all active loans. 2.7 Query optimization in practice. When databases get large, poorly written queries can slow everything down. Optimization techniques. Use indexes on frequently searched columns. Filter early, use where before joining large tables. Avoid select asterisk, request only needed columns. Use execution plans to see how the database processes your query. For example, searching a table with 10 million rows without an index can take seconds or minutes, but with a proper index, it might take milliseconds. 2.8 Database security in practice. Security is not just about locking the door, it's about layer defense. Authentication, verifying who you are, username, password, biometrics, tokens. Authorization, determining what you can do, read, write, delete. Encryption, protecting data in transit and at rest. Auditing, tracking who accessed what and when. Example, in a hospital database, encryption ensures that if someone steals the server, patient data is still unreadable without the decryption key. 2.9 Integrity in practice. Data integrity ensures that the database is trustworthy. Types. Entity integrity, every table must have a unique primary key. Referential integrity, foreign keys must match primary keys in related tables. Domain integrity, values must come from a defined set, e.g., status must be available, borrowed, or lost. Integrity checks prevent invalid, duplicate, or inconsistent data from creeping in. 2.10 Concurrency in practice. In multi-user databases, concurrency control ensures that simultaneous actions don't cause problems. Example. Without control, two librarians might both think a book is available and issue it to different members. With locking and transaction isolation, only one transaction can update that record at a time. Techniques. Pessimistic locking, lock data until the transaction completes. Optimistic locking, allow concurrent access but check for conflicts before committing. 2.11 Database administration. A database administrator, DBA, keeps the system running smoothly. Responsibilities include installing and configuring the DBMS, creating and maintaining backups, restoring data after failures, monitoring performance and tuning queries, managing user accounts and permissions, applying patches and updates. A good DBA is like a ship's captain, nobody notices them when things are smooth, but they are essential in a storm. 2.12 Scaling and performance. As data grows, we must think about scaling. Vertical scaling, adding more power, CPU, RAM, to the existing server. Horizontal scaling, adding more servers and distributing the load. Sharding, splitting data into smaller pieces stored on different machines. Caching, storing frequently accessed data in memory for faster retrieval. 2.13 Troubleshooting common issues. Some common database problems. Slow queries, often fixed by adding indexes or writing queries. Deadlocks occur when two transactions block each other, resolved by careful locking strategies. Data corruption requires restoration from backups. Security breaches require immediate action to isolate and secure systems. We've moved from conceptual understanding to practical application. By now, you should see how database theory translates into real-world systems, from designing tables to writing queries, from securing data to scaling for millions of users. A well-designed and well-managed database is the invisible backbone of almost every modern service, from banking and healthcare to social media and e-commerce. Without them, the digital world as we know it simply couldn't function.